Welcome to Online Precalculus. Today, we're going to cover section P7, Equations. Kind of a longer section here. Our objectives are to solve a linear equation in one variable, solve a linear equation containing fractions, then we'll solve rational equations with variables in the denominator, do a literal equation where we solve a formula for a specific variable, absolute value equations. Then we'll talk about the different types of quadratic equations and how to solve them with factoring, the square root property, completing the square, and the quadratic formula. Then we'll talk about the discriminant and what that means for the number of solutions, figure out the most efficient method to use when solving a quadratic equation, and then finally we'll finish with radical equations. So let's start with a linear equation in one variable. So first, we have to define what a linear equation is. And basically, and you'll see with all the different equations that we solve in this section, the starting point is going to be slightly different. And in this case, we're starting with a x to the first power. Okay, so that's a linear equation in one variable x, and it's going to be written by ax plus b is equal to 0, where a is not 0, right? Because if a was 0, then we would have 0 times x, and that wouldn't be a linear equation anymore. It would just be a constant. So basically what we look for when we have a linear equation, and we're going to have a lot of vocabulary coming up here, what we look for in a linear equation is this variable to the first power. Okay, might have a number in the front, might have another number off to the side, might be equal to 0, could be equal to anything. Okay, so what are we doing with this equation? Well, we're going to be solving it. Okay, so solving an equation in x, determining all the values of x that result in a true statement. And these are called the solutions or the roots of the equation. For instance, right, for our example equation here, if we were to sub in -3, we would get 0. Okay? And that statement right here, that 12 plus 12 is equal to 0, means that -3 is a solution of the equation. We say that it satisfies the equation 4x plus 12 is equal to 0 because if we plug it in, it gives us a true statement. And the set of all the answers, in this case there's only one, but the set of all the answers is called the solution set. And again, -3 is the only number in my solution set. Two or more equations that have the same solution set are called equivalent equations. And what we're going to be doing when we are simplifying 4x plus 12 is equal to 0 is we keep getting equivalent equations, all with the same solution, but we just don't know the solution yet until we get to the last equivalent equation, which is just the variable equal to a number. Okay. The solution set of this equation is the set consisting of whatever number x is equal to. So basically, this is just a long way of saying all the different types of things that we talk about when we solve an equation. We're finding the roots. We're finding the solutions. We're looking for a number that satisfies my original equation. All the answers that satisfy my original equation are called the solution set, and we get that by simplifying my original equation by getting equivalent equations. Okay, so how do we generate equivalent equations? And we can transform an equation into equivalent equations by one or more of the operations. Okay, so we could remove grouping symbols, like distribute a number across grouping symbols. We can add or subtract the same real number from the variable expression to both sides. We can multiply or divide by the same non-zero quantity on both sides. And finally, we can flip the sides around if we wanted to. So we just go through all these different steps trying to make something like that, where we just have x or whatever variable equal to a number. And if we look at the equations in the box, you'll notice that we have solved the equation, by just doing all these steps, right? These are all just the steps of how to solve the equation. Distribute, then subtract 3x from both sides, then divide out the 2, then flip it around. So my final equation with x isolated on the left side shows that just -9 is my solution set because there's no other solutions. The idea of solving a linear equation is to get the variable by itself on one side, usually the left side. Doesn't have to be the left side, right? The -9 is equal to x. It still tells me my solution set. Here's the steps to solve a linear equation in one variable. So we're going to simplify the algebraic expression on each side by removing the grouping symbol, combining like terms. Collect all the variables on one side and all the numbers or constant terms on the other side. Isolate that variable, solve, and then check your answer, right? That's a step that most people omit. But it is a good idea when you get to the end to check your answer to make sure it is correct. And this is actually something we have to do in some later problems. So let's solve a linear equation. My first step was to simplify the algebraic expression on each side by removing the grouping symbols, combining like terms. So I'm going to distribute, and then I'm going to start putting the like terms together. So we distribute the 2, so that's 2x minus 6 minus the 17 is equal to the 13 minus the 3x minus 6. Okay, so there's our, we distributed everything, so we have to combine the like terms. So that's 2x minus 23, the 16 and the 7, is equal to, we're still going to keep this 3x negative 3x. And now we just take the 13 minus 6 to give me 7. Now, when I look at this equation, and I know that my next step is to, I've combined all the like terms, I've removed the grouping symbols. My next step is to collect all the variables on one side and the constant terms on the other side. I always like to bring the smaller variable to the bigger one. So therefore, I'm going to add 3x to both sides instead of subtracting 2x. So this gives me 5x. I'm also then going to, I'm also going to add 23 to both sides. So that gives me 5x is equal to 30. Divide out the 5 to give me x is equal to 6, which makes my solution set x. My solution set is the set of just 6. Now, what you should do next is take that 6 and plug it in to see if it actually works. Times 6 plus 2. So that's 6 minus 3, that's 3. 2 times 3 is 6. 6 minus 17 is equal to 13. 6 plus 2 is 8. Negative 3 times 8 is negative 24. And we get negative 11 on both sides. So this is a true statement, which means that 6 is my solution. Okay, so for linear equations, I'm not going to go through the check each time, but you should probably just double check to make sure that you have the right answer. Okay, let's try one more, our checkpoint. Okay, again, distribute the 4. So that's 8x plus 4 is equal to 29 plus 6x, don't lose the sign there, minus 15. Nothing to combine on the left-hand side. On the right-hand side, we have 29 minus the 15. So we have 8x plus 4 is equal to, we'll just put the 6x first. 6x plus 14. Smaller one goes over to the side of the bigger one. So that's 2x. And then I'm just going to subtract 4 from both sides right here is equal to 10. Divide out the 2. X is equal to 5. Equations are easier to solve when they don't contain fractions. I think we can all agree with that. So if you have an equation that has fractions in it, you probably should try to remove them. And if you multiply both sides of the equation by the least common denominator of any fractions in the equation, this will clear the fraction on both sides. It will clear the equation of all the fractions. Okay, so let's see what we mean by this. Okay. So I have, right, this is also a fraction, right? We can just call that a 1 in the denominator. I have this expression. Let me just rewrite it here so I can mess around with it. Okay, I'm going to multiply everything by the least common denominator. And the least common denominator of this expression, of all the denominators of 4, 3, and 1, is going to be 12. So if I multiply everything by 12 and I distribute the 12 to all three of these terms, or whatever do to one side, have to do the other side. So I need to multiply everything by 12. The 12 over the 4 reduces to a 3. No more fraction. The 12 over the 3 reduces to a 4. No more fraction. And 12 times 2 just stays as 24. Okay? Now we just continue to solve this equation like we would any other linear equation. 3x plus 6 minus 4x plus 4, right, don't lose the sign, is equal to 24. And now we combine the like terms. That's negative x, 3 minus 4, plus 10 is 24. Subtract the 10, positive 14. And I don't want to have my equation, I'm not done, right? I want x is equal to a number, not negative x is equal to a number. So I just multiply both sides by a negative 1. And now I have my answer that x is equal to negative 14. Okay, negative sign should not precede the variable. And of course, you should check it if you want to. A little bit harder here to find the common denominator, but it is, and we could break these down into, or let me write this down. We could break these down into my prime factors if I couldn't figure it out, but I can see that the least common denominator is going to be 28. Right? 4 times 7 and 14 times 2. So 28 over 4 is going to be 7. So that's 7 times x minus 3. That would be 28 over 14 is 2. So that would be 2 times 5, so that's 10. And then minus 28 over 7 is 4, so that's 4 times x plus 5. Careful with the negative sign again. So that's 7x minus 21 is equal to 10 minus 4x minus 20. All right, so combine my like terms. So 7x minus 21, nothing to do over there. The positive 10 minus 20 gives me a negative 4x minus 10 when I combine those like terms. Negative 4 is smaller than 7, so I'm going to add it to both sides. So that's 11x. Add the 21 to both sides. Gives me 11x is equal to 11, so x is equal to 1. And again, if you are unsure of your answer, you should definitely check your answer in the original equation. All right, next is rational equations. So the first couple times we had just x to the first power. Now we might have more, and now we have could have variables on the top, could have variables on the bottom. But my technique is gonna be the same. Okay, so as before. So when we have a rational equation, this is an equation containing one or more rational expressions. So in the last problem, we solved something with just constants in the denominator. Now we're going to have variables in the denominator, but the technique is going to be the same. I'm going to clear the fraction. I'm going to multiply everything by the least common denominator. However, remember that you have to avoid any values that makes the denominator equal to 0. If you get an answer that can't, or if you get an answer that makes the denominator equal to 0, that is not a good answer. It has a name. It is called an extraneous solution. Okay, and we'll see that maybe in the next problem. This one looks like it's going to be okay. So we have 3 over x plus 6. And of course, from section 6, the first thing we want to do is, when I'm trying to add these rational expressions together, is I want it to be factored, right? When I want to try to simplify this. So factors of 12, the subtract of 4, it's going to be x plus 6, x minus 2. Hey, go figure, look at the other denominators. Okay, so now I'm going to multiply everything by the common denominator, which is x plus 6, x plus x minus 2. Okay, and when I do that over 1, all right, I'm just multiplying the left side and the right side, right? I don't have to multiply the top and the bottom. This is not just one expression where I'm trying to combine two fractions. I would have to do that if I'm trying to add these two fractions together. As long as I multiply both of these by all three terms, right, it keeps this equation equal. In the first one, the x plus 6 cancels, and we have 3 times x minus 2 plus, now I just have a 1, so that's x plus minus 2's cancel, x plus 6, and they both cancel on the right-hand side and just give me a 4. So that's 3x minus 6 plus x plus 6 is equal to 4. So that's 4x. The 6's turn into 0. So x is equal to 1. Can x be equal to 1? Well, if I look at this, I should remember that x is just not allowed to be anything that makes the denominator equal to 0. So that would be negative 6, a positive 2, and that's it. So it doesn't say anything about 1, so 1 is a good solution, and that is my answer. Let's try one more of those. So we start with 6 over x plus 3 minus 5 over x minus 2 is equal to negative 20. I'm going to factor this. Guess what it factors to? X plus 3, x minus 2. So I'm going to multiply everything, the left hand and the right hand side, by the least common denominator, which is x plus 3, x minus 2. X plus 3's cancel, and we get 6 times x minus 2 minus the 5 times x plus 3, and that equals negative 20, because they both cancel on the right-hand side. 6x minus 12 minus 5x minus 15 is equal to negative 20. Negative 6 minus 5 is x. Negative 12 minus 15 is 27. Add that to both sides, and so x is equal to 7. Go back to my original equation, and x is not allowed to be negative 3 or 2. So 7 is okay. For this one, same idea here. Let's factor first, x plus 1, and multiply by my common denominator. So that's 2 over x plus 1, x minus 1, as I factor the difference of two perfect squares, minus 1 over x minus 1. Okay, so now I take this entire expression, and I'm going to multiply by the common denominator, x plus 1, x minus 1. X plus 1's cancel, So I have x minus 1 is equal to, both of them cancel, 2 minus x minus 1's cancel, x plus 1. Okay, so I have x minus 1 is equal to 2, distribute the negative, negative x minus 1. Add that to both sides. So 2x, add 1 to both sides, and I should have put it with that one, but I can just cancel those two. So 2x is equal to 2, x is equal to 1. I should be happy. I got an answer. But if you look carefully at the original problem, we should notice that x is not allowed to be equal to plus or minus 1. So this answer of 1 is no good. So that means that there is no solution to this problem. That just means the two sides will never be equal. Okay? Do that again with our checkpoint. Probably the same thing's going to happen. Let's see. 1 over x plus 2 is equal to 4 over factor x plus 2, x minus 2, minus 1 over x minus 2. Okay? Multiplied by the common denominator, x plus 2, x minus 2. And before I even start, right, I should think that x is not allowed to be equal to plus or minus 2 when I'm done. Okay, so 1 times those two cancel with the x plus 2. So we have x minus 2 is equal to, both of them cancel there, minus x plus 2. Distribute the negative. Combine the like terms. Negative x minus 2. Add that to both, whoops. Add the x to both sides. It's 2x, add the 2. And unless I did something off here, we got x is equal to 0. Well, can I put a 0 in the denominator? Well, I can't make the denominator equal to 0, but I can plug in 0 into these things. So not sure if I made a mistake on this one to give me undefined. Let's double check here. Plus 2, distribute. Two x. I don't see it, but maybe somebody watching this will see it later. Okay, so the answer is either 0 there, or if I were to get 2x is equal to 4 and x is equal to 2, then it would have been undefined. Okay, so solving a formula for a variable means rewriting the formula so the variable is isolated on one side of the equation, the variable that you want to be isolated. You're not going to get a number. You're just going to be rearranging a bunch of stuff until you get what you are looking for. So in this example, if you wear glasses, did you know that each lens has a measurement called its focal length f? Okay. When an object is in focus, its distance from the lens p and the distance from your retina q satisfy that formula. 1 over p plus 1 over q is equal to f. Solve this formula for p. So in my answer, I want p equal to, something. All right. What that something is, that's what we're about to figure out. So let's keep manipulating this formula until I have only a p on the left or right, only a p and no other p's anywhere else. Well, before I do this, I got to put those two fractions together. So a common denominator would be p times ugly q, p times q. So numerator would turn into q plus p is equal to 1 over f. Okay. Let's clear the denominators So that way I can deal with things that are not fractions. So I'm going to multiply everything by P, Q, F. P and the Q cancel, so now I have F times Q plus P is equal to P times Q. Okay, distribute. FQ plus FP is equal to PQ. Remember my goal here is I want P by itself. Okay, so that means that everything that has a P in it, I'm going to move it to the left side, and the other one I'm going to put over on the right. So I have FP minus PQ, right, if I subtract that from both sides, equals negative FQ, if I move that one over there. Now I can collect all the P's together by factoring. F minus Q is equal to negative FQ. And finally, isolate the P by division. And so P is going to be equal to negative FQ over F minus Q. And, you know, if I wanted to, I could also factor out a negative so I don't have so many negatives here and make this FQ over Q minus F, change the sign of everything, make it a little cleaner. But, you know, you didn't have to do that. And that would have turned out if you had just moved everything to the right-hand side instead of to the left. Okay? But the point is we managed to get P by itself and isolate that particular variable. Okay? So again, same technique. In fact, this is the same question. It's only you're solving for a different letter. So again, same idea is put them together. PQ, Q plus P with the common denominator, 1 over F. Multiply everything by the common denominator, PQF. So that turns into FQ plus P equals PQ. Let's go to the right this time. FQ plus FP is equal to PQ. I'm trying to solve for Q, so I want everything with a Q on the right. Okay, so I have FP is equal to PQ minus FQ. FP, factor out the Q, P minus F, and we then divide it, P minus F, divide it out. So FP over P minus F is equal to Q. So same idea, same general technique of putting the fractions together, clearing the fraction with a common denominator, and then just doing a little bit of algebra to get the variable by itself. Confusing because there's no numbers here. It's not really like something that you can see when you're solving it, but you just have to keep your goal in mind and figure out which variable you want by itself. All right, so next type of equation, that was called a literal equation, by the way, or solving a formula for a variable. All right, so the next kind of equation we have is something with absolute value. So we've seen that the absolute value of x with the absolute value bars, all right, I should know my symbol for absolute value. It describes the distance of x from 0. So if you think about an absolute value equation where the absolute value of x is equal to 2, if I think about that on a number line, well, here's 0. 2 is 2 spaces away from 0, but also negative 2 is as well. Okay, so there's going to be 2 solutions to this equation. And the way you solve it is you just rewrite the equation without the absolute value bars. And the way you do that is you consider both cases. Inside of the absolute value could be 2 choices, negative 2 or positive 2. After I take the absolute value, it is going to be positive. So when we are rewriting an absolute value equation without the bars, we take whatever's in the absolute value and we make two separate equations. U is equal to C or U is equal to negative C, because the absolute value would make both of those true in the equation U is equal to C. So what does that mean? It means we isolate the absolute value bars first, and then we split my equation into the two cases. This is what I mean. So we isolate the absolute value bars first. So we have 5 times the absolute value of 1 minus 4x is equal to 15. Don't distribute into the absolute value. Just divide out the 5. Get the absolute value bars by themselves. Now we can split this into two equations. The inside of the absolute value could be 3, or the inside of the absolute value could be negative 3, and the absolute value would still be equal to 3 once it's done. So when I remove the absolute value bars, I just consider both cases. Subtract the 1, negative 4x is equal to 2. Divide out the negative 4, so x is equal to a negative 1/2. Subtract the 1, negative 4x is equal to negative 4, so x is equal to a positive 1. Okay, it is okay to get a negative answer for an absolute value equation, right? If you want to check, you can plug it back in and they will both actually work. Let's try it again. Same idea here. Add 20 to both sides. 4 times 1 minus 2x is equal to 20. Divide out the 4 to isolate the absolute value. Then split it into two cases, the positive case and the negative case. Subtract 1, negative 2x is equal to 4. Divide out the negative 2. And subtract 1, divide out the negative 2. X is equal to a positive 3. Now, it is important to mention that the absolute value of a number is never negative. Thus, if U is an algebraic expression and C is a negative number, then the absolute value of U has no solution. For example, that 3 minus 6 equals negative 2 has no solution because absolute values cannot be equal to a negative number. Back to my problem right here. If this was a positive 20, this would be negative and this would be negative, and now you would have no solution. The big mistake people usually make is, oh, they put that one negative and that one positive, and they try to solve for the absolute value just like you were doing. Then you would get the same thing, right? You'd get probably the same thing, but it wouldn't be correct, and you would have had all that work for nothing, right? If you have an absolute value equal to a negative number, there is no solution. This is a very common trick question. Absolute value of 0 is 0. So if you have the absolute value equal to 0, you don't have to split it into two separate equations. There's only one solution in that case. But the more common trick is absolute value equal to a negative number. So be careful of that. Okay, so next, let's start talking about quadratics. So linear equations, all the equations we've done so far have been first degree, right? The absolute value, everything was x to the first power. The rational ones had a couple things that we factored into x to the first power, but we haven't had to deal with anything that's x squared too much yet. Okay, and these are going to be called quadratic equations, which are second degree polynomial equations and contain an additional term involving the square of a variable. So quadratic equation is typically written in general form as ax squared plus bx plus c is equal to 0. Where a, b, and c are real numbers, a can't be 0 because if it was, this would just be a linear equation. It wouldn't be a quadratic equation anymore. It's not saying that that's bad. That's actually easier. But here are a couple of quadratic equations in general form. You can have the other letters be 0, right? C is 0 in the first one. or you could have numbers for each of them. The easiest way to solve a quadratic equation is with factoring, and both of these two expressions can be factored. In fact, I think we'll factor one of them in a second. If you can factor it, you can solve it using something called the zero product principle. And the zero product principle says that if the product of two algebraic expressions is zero, then one of the factors has to be zero. So if you can set a factored quadratic equal to zero, then one of those two factors must be equal to zero, and you can separate them and solve them separately. Okay? This only applies when a quadratic is in general form equal to zero. And then, after you factor it, you can solve the two equations. So, how do you solve a quadratic equation by factoring? Rewrite it so it's equal to zero, moving all the terms to one side so you get zero on the other side. If you don't do that, it's not going to work. Factor, zero product principle, setting each factor containing a variable equal to zero, solve, and of course, check your answer if you want to. All right, so like I said, now let's solve some of these by factoring. So what can you factor out of this expression? It's got no c. We're not going to do any of our more difficult techniques. All we're going to do is use the greatest common factor. So we can factor out a 2x, and we're left with 2x minus 1. Set that equal to 0. This is a product equal to 0. That means the first term or the second term has to be equal to 0. So x is 0, or add 1 to both sides, divide out the 2, x is equal to 1/2. And those are my two solutions. Plug them back in, and you'll get either one of them to work. Okay, so my solution set is the set of 0, 1/2. Both of those are answers to this equation. And it is possible, like we saw in the last ones, to get more than one answer. Here, I don't like this setup the way it is. So the first thing I'm going to do is 2x squared plus 7x minus 4 is equal to 0. Now I'm going to factor with my trial and error method, guess and check. So we're going to put a 2x there. I'm going to put an x there. The factors of 4, whose inside terms and outside terms subtract to give me 7, or add up to a positive 7. So if I put a 4 here, a positive 4, that's 2 times 4, that's 8, minus the 1 is now a positive 7. So now each one of these terms can be set equal to 0, which makes x here a positive 1/2 and x here a negative 4. Again, checking both of those, they would both work. Okay, let's try our checkpoint problems again. Same two techniques. So for A, we're going to factor out a 3x, which leaves me with x minus 3. So x is going to be 0, and x is going to be 3. For part B, I'm going to have to first subtract 1 from both sides to give me this expression. Then I'm going to factor it, 2x and x. I want a negative 1, so I want a, how about a plus 1 there, minus 1 there, and that works out. So x would be 1/2 again, and negative 1 for my other two expressions. So that was solving by factoring. Sometimes things are not going to factor, okay? Or sometimes there maybe is a slightly easier way to solve a square root equation, and one of them is the square root property. So if I just have something squared, a variable squared, equal to some number, and it doesn't have to be just one thing on the left-hand side, it can be a whole algebraic expression, as long as it's a perfect square equal to a positive real number, then we can solve this with the square root property. First, isolate my expression on one side, and then take the square root of both sides. And remember, when you take the square root of both sides in equations, we have to take the two cases, the positive and the negative, right? Because both of them squared would be equal to a positive number. You can verify this if you wanted to by factoring and using the difference of two perfect squares. Factor into two conjugates, and you can see that you get the two opposite answers. And so because the solutions differ only inside, we can write them as plus or minus. It's just a little shortcut. So it equals to positive or negative square root of d, or plus or minus square root of d. Either way you want to say that, it's fine. And this is called the square root property, and you can see it down here too. So if you use an algebraic expression and d is a positive real number, then u squared equal to d has exactly two solutions, square root of d and negative square root of d, or plus or minus square root of d. So, and you can solve this equation with a different technique, but if we're going to use the one we just talked about, we can say, oh, look, there's this x squared, there's no other variable. If I can get the x by itself, then I could just take the square root of both sides. So now, as opposed to some other problems, we don't want it equal to 0. So we have 3x squared is equal to 15. Divide out the 3. We now have x squared is equal to 5. Taking the square root gives me my two solutions. X is equal to plus or minus square root of 5. Okay, this also works if you have a binomial perfect square. You could, if you wanted to, square this and then subtract 6, that is equal to 0, factor, try to solve. Wouldn't factor, but you could use other techniques. Or just right from here, take the square root of both sides. That's x minus 2 is equal to plus or minus the square root of 6. Adding 2 to both sides gives me x equals 2 plus or minus the square root of 6. All right. And those are my two solutions, 2 plus the square root of 6 and 2 minus the square root of 6. Let's try those again. Again, first one, adding 21 gives me 3x squared is equal to 21. Divide out the 3 to give me x squared is equal to 7. Square root gives me x is equal to positive or negative radical 7. Here, just boom, just jump right into it. X plus 5 is equal to plus or minus square root of 11. Subtract the 5 from both sides. X is equal to negative 5 plus or minus the square root of 11. Okay, so as long as you have something squared on the left, you can use this property, square root property. Next, we have what to do if we have an equation in standard form and it can't be factored. Okay, so now we have this other variable. We can't just use the square root property. We're going to need something else. So we're going to have two methods here, right? From the title, quadratic equations, completing the square. The first one is going to be called completing the square, which will lead to how to get the quadratic formula, which would always work. So completing the square is if you have x squared, notice, if you have x squared, not ax squared, just x squared. So you're going to need to have a leading coefficient of 1 to use this technique. And it's a binomial, which we can always make everything a binomial by subtracting off the c. Then we add b squared over 2, which is the square of half the coefficient of x. And if you do this, you get a perfect square trinomial. So if we take this middle term, or if we take this term next to the linear term, the coefficient next to the linear term, if we take that, divide it by 2, and square it, the resulting trinomial will be a perfect square trinomial. We can solve any quadratic equation by completing the square. And like I said before, if the if the x squared term is 1, okay, and then we add the square of half the coefficient of x to both sides of the equation. When you add a constant term to one side of the equation to complete the square, be sure to add it to the other side. So we're just adding this to make something squared. We're going to have to put it on the other side of the equation. So what does that mean? It means if we have this equation right here, so if we have x squared minus 6x, I'm going to move the 4 over to the other side. Okay? My goal now is to just make up a number that would make this on the left a perfect square trinomial. Well, what number is that? Well, 6 divided by 2 is 3, squared is 9. That is now a perfect square trinomial. But if I add 9 to the left, I have to add 9 to the right as well. Now I can factor this. For negative 4 plus 9 is 5. Now take the square root of both sides. X minus 3 is equal to plus or minus square root of 5. Adding 3 gives me my two solutions, 3 plus or minus the square root of 5. Let's try that one more time. Solve by completing the square. First, we want x squared plus 4x. I'm going to move the 1 to the other side. I'm going to leave room right there. 4 divided by 2 is 2. Squared is 4. Now that's a perfect square trinomial. And remember, it's always when we are trying to figure out what to add to both sides, it's always this term divided by 2 squared. There it is. So we now have x plus 2 squared. But remember, if I add 4 to this side, I have to add it to this side as well. Square root both sides. We have x plus 2 is equal to plus or minus square root 5. Subtract the 2, and we get negative 2 plus or minus the square root of 5. So now, normally I would go through all these steps, but I don't want to make this video forever. It's already getting pretty long already. But you can use the method of completing the square to derive a formula that can be used to solve all quadratic equations. And this is called the quadratic formula. So the derivation here shows a general form on the left and this specific example on the right on how to go about solving the quadratic formula, or how to figure out getting the two solutions, generally and specifically. Now, I wouldn't do these steps every time you're trying to solve something using this technique. I would jump right to the formula at the end. So basically, we start out with a general equation. We would divide out the a in order to use the technique of completing the square, and you can see that right here. We would then move the term to the right-hand side. Okay. Then we complete the square. Right. We take b over a. Half of it is b over 2a squared, and I add it to both sides. Then I just square that term in order to make it, easier to work with. Now, this whole thing factors into that expression, x plus b over 2a squared. And now I want to put these two fractions together, so they need to have a common denominator. So that's what that's doing right there. Factor common denominator on the right-hand side. Now, right, look what we have. 4ac and a negative 4ac. We have a b squared all over this. And I can just rearrange it. And now taking the square root of both sides, the numerator really doesn't, right, we're left with out the square term now. The numerator really doesn't simplify, but the denominator, 4a squared is a perfect square, is 2a. And then we just subtract this from both sides, and now we have our final formula. So again, you could do that all with a specific example to get down to your answer. Or we just remember the quadratic formula. Okay, so the quadratic formula, negative b plus or minus the square root of b squared minus 4ac all over 2a, is the quadratic formula. And this, as you can see, no matter what we start with, any quadratic, this formula will work. Okay? Not always the most efficient method, not always the easiest method to use, but always a fallback if you need to solve a quadratic, but you are not sure if it factors and you're not sure what else to do with it. Okay? To use this formula, we write the quadratic formula in general form. Okay, look, it does equal 0, so we have to put it in general form, and we determine the numerical values for a, b, and c, and then substitute the values into the quadratic formula to get my two solutions. So this expression is already set equal to 0. We just say that a is 2, b is a negative 6, and c is 1. The quadratic formula is negative b plus or minus the square root of b squared minus 4ac all over 2a. Helps if you can't remember it, helps to sing it a little bit, maybe to the tune of something like Pop Goes the Weasel is the most famous one. Negative b plus, I don't want to do the whole thing. You get the idea. You can watch that on YouTube if you want. So we have negative 6 plus or minus the square root of negative 6 squared minus 4 times 2 times 1 all over 2 times 2. All right, let's simplify this. Negative 6, negative 6 is positive 6, plus or minus square root of 36 minus 8 over 4. Okay, well, 36 minus 8 is 28. So that's 6 plus or minus the square root of 28 over 4. Now, we don't want to turn this to a decimal. Okay, we definitely want to just keep simplifying this as much as possible. So in order to do that, I'm going to simplify the radical, okay, which 28 is 4 times 7. So that's going to be 6 plus or minus 2 square root 7 over 4. And then we can finish this by dividing out a 2 from everything, right? We can factor out a 2 from the numerator and the denominator, and they will both cancel. So my final answer would be 3 plus or minus the square root of 7 all over 2. And that's two answers, 3 plus square root of 7 over 2 and 3 minus square root of 7 over 2. But typically, you can just write it using the plus or minus sign. Let's try it again. It's our checkpoint problem. All right, so A is 2, B is 2, C is negative 1 for my quadratic formula, right? A is always in front of the x squared, B is always in front of the x, C is the constant term, including all of the signs. So x is equal to negative b plus or minus the square root of b squared minus 4 times a times a negative 1. Careful with the signs here. Okay, sometimes it can get a little tricky if you have some negatives in there, and over 2 times a, which is just 4. So that's negative 2 plus or minus the square root of, let's be careful with this, it's 4 minus negative 4 times 2 times negative 1. So that's a positive. So that changes to a positive. 4 times 2 times 1 is 8 over 4. So that's the square root of 12. So that's negative 2 plus or minus square root of 12 simplifies to 2 square root 3 over 4, which makes my answer a negative 1 plus or minus the square root of 3 over 2 as I reduce. All right, so let's finish talking about quadratics, or wrap this up kind of with something called the discriminant, which is the quantity that appears underneath the radical sign in a quadratic formula. This tells you how many types of solutions you will get and what they look like. Now, as we'll look in chapter 1 and 2, is if we have a quadratic with an x squared, we're always going to have two solutions. But sometimes they're going to be two unequal real solutions. Sometimes they're going to be two repeated solutions. And sometimes there are going to be no real solutions, which means two imaginary solutions. Okay, so no matter what, we're going to get these two solutions, but the discriminant can tell us what kind of solutions they would be. Two unique real, a repeated solution that's a real number, and no real solutions. Okay, and that depends if the discriminant is positive, and the discriminant is the part underneath the radical. So can you take a square root of a number bigger than 0? Yeah. When you take the square root of 0, you get 0. And when you take the square root of a negative number, you get imaginary numbers. So using the discriminant, what does it tell you about the number and type of solutions? So remember that the discriminant is b squared minus 4ac, not the radical, right? Just the part under the radical. So that's going to be negative 8 squared minus 4 times 4 times 1. So negative 8 squared is 64 minus 16, which doesn't even matter what it is, 48, because it's positive, which means you will get two real solutions, both not equal to each other. Real unequal. Two real unequal solutions. For this one, right, again, we have b squared minus 4ac, which would be b squared would be, let's just write it out, negative 2 squared minus 4 times 3 times 5. So that's going to be 4. And look at this. 4 times 3 times 5 gives me 60, which makes this a negative 56. So that is no real solutions. Right? There would be two imaginary, but we're not really there yet. So no real solutions. Okay, so after all of this with quadratics, right? So that was a lot of different quadratic formulas, a lot of different types of quadratics. Which way is best? All right, all of them can be solved with the quadratic formula, right? That's the first line. All quadratic equations can be solved by the quadratic formula. However, sometimes it is faster to use the square root property. Sometimes it's faster to factor. So because we use a method in completing the square to derive the quadratic formula, that's not really super useful for solving quadratic equations. It's okay, and we can use it to help graph circles later, but we're really not going to use it too often to solve quadratic equations. So which method should you use? So the most efficient method is if you see a quadratic that can be factored easily, factor it, set it equal to 0, set the factors equal to 0, and use the zero product principle. If you don't have a c, right, if there's no c, always factor, right? And you can tell by the example there, it is very easy to just take out a GCF. If there's no b, right, if b is equal to 0, use the square root property. Just isolate the x squared, take the square root of both sides. If it's not even just a b equal to 0, if you have some term squared, right, same thing, use the zero product property. And finally, if you cannot factor it or you cannot figure out how to factor it, that's when you fall back to use the quadratic formula. Okay. So again, there is definite steps you should take when you look at this. Is first look at these two. Are you missing a term? If you're missing a term, then use one of those two techniques, right? Either GCF or the square root property. If you're missing the a, it's not a quadratic. To solve it, it's a linear equation, right? So you can't be missing the a to be a quadratic. Then see if you can factor, and then finally quadratic formula. Okay, so let's finish this section with a radical equation. So unlike a quadratic, which had x squared, a radical equation is when the variable occurs in a square root or any other higher root, like x squared is equal to 9. So when you square both sides to eliminate the square root, you don't now have to put plus or minus, okay? But when you do square both sides, you could introduce extra solutions, okay? You should definitely check your work, right? Because square root of 81 is equal to 9, the solution is 81, and the solution set is the set of 81. So in general, we solve radical equations with square roots by squaring both sides in the equation, and we solve nth roots by raising it to the nth power, whatever the root happens to be. Okay, so if it's the third root, raise it to the third power. But if n is even, all the solutions of the equation raised to an even power may not be solutions of the original equation. For instance, we have x is equal to 4. So remember that, x is equal to 4. If we square both sides, you get x is equal to 16. Try to go back to that and take the square root of both sides. You would get plus or minus 4. No good, right? Because we only had one solution. Now suddenly we have two solutions, okay? So when raising both sides of an equation to an even power, you must always check your solutions to see if you got an extra solution, especially if you have variables on both sides, okay? So how do you solve a radical equation? If necessary, arrange the terms so that one radical is isolated. Raise both sides of the equation to the nth power to eliminate the root, and then keep going until you get rid of all the radicals. And check your answers, especially if there are variables on both sides. Especially if there are variables on both sides. Okay. Again, this probably will have an extra solution. So let's check it out. First, I got to isolate the radical. So first, I'm going to subtract 2 from both sides. Square root of 2x minus 1 is equal to x minus 2. Oops. All right, now I'm going to square both sides of this equation to give me 2x minus 1. That was the point of squaring both sides. This gets rid of the radical. Over here, we have to FOIL this together. So that's x squared minus 4x plus 4. And I now have a quadratic. I now have x squared. Well, from my previous work in this whole section, I should realize that I should set it equal to 0. So I'm going to subtract 2x from both sides and add 1. I'm going to subtract 2x and add 1 to give me x squared minus 6x plus 5. The easiest way to solve a quadratic, if it has all three terms, is to factor it. This does factor quite easily to x minus 5 and x minus 1, which makes my answers 5 and 1. Let's put them separately. Okay. However, you must check to see if they both worked. We raised this to an even power. You have to check to see if your solutions work. So we have to go back to my original equation and say, could the answer be 5? The square root of 2 times 5 minus 1. 2 times 5 is 10, minus 1 is 9, and this better be equal to 5. So that is 3 plus 2, that's 5. This one works. Good. Well, let's try with the 1. Okay, so 2 times 1 is 3, minus 1, 2 times 1 is 2, minus 1 is the square root of 1, plus 2, is that 1? No, it is not. Okay, so that is 3 equals to 1, which is not true. Okay, so by squaring both sides here, we definitely introduced an extra solution, which we couldn't even tell, right? They're both positive. They both seem like good answers. So you do have to check. So let's try again. And especially, you have to recognize that if you have the variable on both sides, it is very possible to get a extraneous solution. Subtract 3 from both sides. We have the square root of x plus 3 is equal to x minus 3. Squaring the two sides is x squared minus 6x plus 9. I see an x squared, so I'm going to set this equal to 0. Subtract x, subtract 3. We have 0 is equal to x squared minus 7x plus 6, which does factor nicely to x minus 6, x minus 1, which makes x 6, and x is equal to 1. Plugging in a 6, that's 9. Square root of 9 is 3. 3 plus 3 is 6. That's good. Plugging in a 1 gives me 4. Square root of 4 is 2 plus 3 is not 1. It is 5. So my answer is only the 6. So we covered a lot of different types of equations. We covered linear equations. We covered equations with fractions in them. We covered rational equations where we had to clear the denominators by multiplying by a least common denominator. We solved formulas for variables. We did absolute value. We did a bunch of different types of quadratics. And then we finished with a radical equation. Okay? So this was section P.7 Equations.